Hi, everyone. In lesson 15, we're going to discuss discrete probability distributions. What is possible and what are the chances? So we're going to let X, remember him? We're going to let X be a quantitative random variable. For example, in example 1, if you roll a standard six-sided die, let X be the result of that die. Now, before you roll the die, the value of X is basically a number that is not yet known. We have not yet rolled the die. However, we can know its probability distribution, assuming that the die is an ideal standard die. Ignore the issue with the holes and all that. Assume that it's an idealized standard die. Well, we then know its probability distribution, which would give the possible values of X and their corresponding probabilities of occurring. So for example, if you're rolling a six standard die, what are the possible values of X and what are the corresponding probabilities? Assuming that the die is perfect. Well, X has the following discrete probability distribution. The possible values are nicely listed. They're listable, they're countable. That's why we call it a discrete distribution. The possible values of X are boom, 1, boom, 2, boom, 3, boom, 4, boom, 5, and boom, 6. We can cleanly list these possible values, unlike for a continuous distribution on, for example, weights or heights. The corresponding probabilities will all be equal, 1/6 apiece. What do you call this kind of distribution when the probabilities are all equal? Starts with U. That's called a uniform distribution. All the probabilities for all the possible values are equal. We'll talk more about uniform continuous distributions later on. Now, the distribution of X can be described by a formula. Here, it's very straightforward. The formula here would just be P of X equals 1/6, as long as X is either 1, 2, 3, 4, 5, or 6. That's the formula for the die. So the distribution may be described by a formula, a graph. So we might use bars in this case, like a probability histogram. So we have here the numbers 1 through 6. And each bar would have height 1/6. Each width would be 1 unit. A probability histogram. Equal probability for each of the possible 6 faces on the die. One-sixth apiece. Now, if you actually roll a die, you'll get some sampling error, but these are the probabilities. A uniform distribution for a die. All right, or a table, like so. All right, so again, a probability distribution may be described by a formula, like this, by a graph, like a probability histogram, or a table, like so. All right. Now, a discrete probability distribution, and again, a discrete probability distribution is one in which the possible values for the random variable can be listed in a table, like so. The integers from 1 through 6. A discrete probability distribution must have these two characteristics. Well, the numbers over here must be actual probabilities. They have to be real numbers between 0 and 1. They must be real numbers between 0 and 1. You can't have negative numbers or probability or numbers like 2 or 3. And all the probabilities must add up to 1. So you must indicate all the possible values, and the corresponding probabilities have to add up to a sum of 1. If there's round-off error, there's round-off error. All right, so for example, let's say that an office has 4 computers, and any number of them might break during the week. We will randomly select a 5-day future work week for the office. Ignore holidays and all that. Let X be the number of computers that need a repair during the week. the IT manager for the office gives you the following incomplete probability distribution for X. So the IT manager is basically saying here that the probability of one computer being broken in that week is 20% or 0.2. So P of 1 here, that's the shorthand, P of 1 is 0.200 or 20%. Likewise, the probability of two computers needing a repair is 10% or 0.1. The probability of three computers needing a repair is 4% or 0.04. The probability of four computers, all four computers needing a repair, is 1%, 0.01. Your task, find A. That is, find the probability of none of the computers needing a repair, assuming that these other probabilities are accurate. Find A, the probability that none of the computers need a repair that week. Find P of 0. So what would you do? Well, what is the total probability? What do the sum of these have to be? The sum of these will have to be 1. So to solve for A, we subtract these other probabilities from 1. The sum must be 1. So A is going to be 1 minus this, and this, and this, and this. You subtract all these from 1. And the answer turns out to be 0.650. So there's a 65% chance that none of the computers will need a repair during that random week. All right. So that's P of 0. And that's often a convenience. So if you're just missing one probability, but you know the others, what you can do is you can subtract the other probabilities from 1 and get the desired probability. This comes up a lot in the idea of complements, finding the probability of a complement. So if you want to know the probability of this, find the probability of the complement, which is the sum of these over here. So these are complementary events over here. These represent complementary events. And then you can find the probability here, the A, because these have to add up to 1. All right. Now, a lot of people have trouble with the wording of inequalities. And in a way, this is a skill that's even more fundamental than a statistics class. It's a matter of proper English and understanding terminology in pre-algebra. Wording of inequalities. We're going back to the previous example. So we're plugging in P of 0, which was 0.650 over here. We've done that. Based on this probability distribution table, all right, write the following as inequalities, rewrite them as a sum of probabilities, and calculate the indicated probability. So for example, the probability that at least one of the computers will need a repair. First of all, what does at least one mean? We have to ask two questions. Okay, so at least one, what does that mean? First of all, do we include one? Does at least one include one? If we say a family has at least one child, is it possible that the family just has one child? Yes, at least one does include one. I'll put a solid dot here and label it a 1. And then, do we want greater numbers or lesser numbers? At least 1. If you're told to be eligible for financial aid, you have to take at least one class. Can you take more or fewer? You can take more. So, what does at least 1 mean in this table? It means that one computer could be broken, or 2, or 3, or all 4. And to find this probability, we have to add the corresponding probabilities over here. Also, what's a quick way of calculating this? I mentioned the idea before. Consider the complement, the probability that no computers are broken. Its probability is 0.650. So a quick way of finding the desired answer is to just take 1 minus 0.650. So you could, of course, add all of these up. That's fine. You could take the sum of these, add these all up. That would work. But it's easier and you're more likely to get the correct answer. You're more likely to be accurate if you take 1 minus this, which is 0.350. All right. Okay. Now, again, over here, at least one, do we include one? And do we go higher or lower? Two questions to ask as you run through the semantics of these, the wordings of these. So I'll give you a minute to work out these 3 other problems. B, the probability that more than one computer will need a repair in that week. C, the probability that at most 2 computers will need a repair in that week. And D, the probability that fewer than 2 computers, that's more proper than saying less than 2 computers, will need a repair in that week. And these are the kinds of questions you should ask yourselves. Do we include these boundary values or do we exclude them? And then do we go higher or lower? I'll give you a minute to figure out the corresponding relevant values of X here, work out the probabilities, add up the relevant probabilities, or maybe do a complement trick and compute the probabilities. And also try to remember how to rewrite these using inequalities. So here are the instructions. Rewrite these using inequalities, rewrite as a sum of probabilities, and evaluate and calculate the indicated probability. For part A, I forgot to do these parts. I'll go ahead and do that now. In part A, how do you rewrite using an inequality? I want the probability that X, the number of computers that will need a repair, will be at least 1. Now, at least 1 means greater than 1 or possibly including 1. Put a bar there. The probability that X is at least 1. The probability that X is greater than or equal to 1. That's how you would write it in an algebra class. And then what are the corresponding probabilities? What do we add up? We would add up P of 1, the probability of 1 computer breaking, plus P of 2, plus P of 3, plus P of 4, the probability of all 4 computers breaking. Or more easily, it's good to know that you can also think of this as, you could also compute this as 1 minus P of 0. Use the complement trick. Take the complementary probability, subtract from 1. That's what I did over here. So for B, C, and D, rewrite using an inequality, rewrite as a sum of probabilities, maybe consider using this complement trick, and calculate the indicated probability. I'll give you a minute. All right. So what's the probability? Let's repeat. What's the probability that at least 1 computer needs a repair? Here's the table down here. All right. Again, repeating part A. At least 1. All right. So that's a probability that X is greater than or equal to 1. Over here is the sum of these probabilities. Here I list the probabilities. On your homework, do either this or this. You don't have to do both, but do either this or this, and then give the final answer, 0.350. On B, and again, you could use the complement trick over here, 1 minus P of 0. On B, the probability of more than one computer needing repair. Does more than one include one or exclude one? It excludes one. More than one excludes one. And then do we go higher or lower? We go higher, greater than one. The probability that X is strictly greater than one, so we want the X values of the X values of 2, 3, and 4. We don't want the 1, certainly not the 0. Okay? We want these corresponding probabilities and add them up. All right. So the probability that X is greater than 1 is going to be P of 2, which is this, plus P of 3, plus P of 4. I list the probabilities. When you add them up, you get 0.150. By the way, for some people, it might be faster to take 1 minus this minus that. The idea of the complement. The complementary probability is 0.850, so the probability you want is 0.150. Well, you could do the complement trick here also. 1 minus this minus this. How about the probability of at most 2? At most 2 includes 2, and we go lower. At most 2 includes 2, and we go lower, 1 and 0. The probability that X is less than or equal to 2, that's P of 0 plus P of 1 plus P of 2. Add up the probabilities, you get 0.950. So you want 2 and everything below it. Or you could go 1 minus that minus that. That's also legal. Or 1 minus the sum of these. You could take the sum and subtract off that from 1. All right. The probability of fewer than 2. We exclude 2, so I might put an open circle here. We exclude 2. We exclude 2, and we go lower. We move towards lesser numbers. So for fewer than 2, we don't want 2 itself, but we want X equals 1, also X equals 0. We add up these probabilities. The probability that X is less than 2, strictly less than 2, no bar, we don't include 2. This is P of 0 plus P of 1. You add up these two probabilities, and we get 0.850. Okay, next we're going to use these kinds of tables to talk about things like long-run averages and expected values.